Hello everyone, and welcome to today's lecture. So today's lecture will be a quick lecture on two very important comparison tests for judging the convergence or divergence of infinite series. And luckily these tests are very similar to two previous tests that we studied for improper integrals. These are the so-called direct comparison tests, the direct comparison theorem, and the limit comparison test, the limit comparison theorem. The wording of each of the tests is actually almost exactly the same as it was for the improper integrals of functions. But these are going to be for infinite series. But both of the tests, in the way that they're applied, is in some sense very, very similar, if not exactly the same as it was for improper integrals. So I'm going to start by writing both of these two tests down. The first one will be the direct comparison test. And this is now, of course, infinite series. And what we're going to do is assume that we have two separate series. And furthermore, we're going to assume that the terms in these series are positive, in that the terms in the first series AK, so each term in this series AK is going to be less than or equal to BK for all K in these infinite series. So if these two assumptions are true, then we can say directly the following two things. If the series of the BKs converges, so the upper bound for each one of the AKs, if the sum of all of these BKs converges, then the sum of the AKs must also converge. And on the other hand, if the sum of the lower bounds, the sum of the AKs, diverges, then the sum of the BKs, which are the upper bounds, must also diverge. And you'll remember that this statement was almost exactly the same when we were applying the direct comparison test for improper integrals. But now this is for series, for infinite series. But what's kind of really neat here is that this also, directly holds for infinite series. And the reasoning behind this is very much similar to the reasoning behind the direct comparison theorem for improper integrals. And so the proof of this theorem is relatively straightforward and can be found in the book. What I'm going to do is just kind of go over a couple of different examples of how to apply this theorem, and this should hopefully suffice to show you how to use it. So suppose that we have a relatively complicated looking series. Let's say the series from k equals 1 to infinity of k plus sine of k divided by k cubed plus 1, which going through and solving for whether or not this series converges would be kind of difficult to do. Very, very difficult, in fact. And so these tests, just like before, are going to help us determine whether or not the series converges without giving us the actual value of the series. So this is what we're trying to do, just trying to figure out if this series converges to a real number or if it diverges. And so what we need to do and look at is, when we're applying the direct comparison theorem, can we bound this above or below by something that is a simpler series? And so what we're going to do is, just like before for the direct comparison theorem here, k is between 1 and positive infinity. And what we need to do is look at the actual series terms. So this is k plus sine of k over k cubed plus 1. And the first thing that we have to verify is that this is always positive if we're going to apply the direct comparison theorem, which is certainly true because when k is between 1 and positive infinity, you know that sine of k will always be bigger than negative 1 or equal to negative 1. And because k starts at 1 and is always greater than or equal to 1, this numerator term is always going to be positive. And same thing with the denominator term, because k is between 1 and infinity. So this is verified. And now we need to find an upper bound for this series. If you do the rule of thumb, right, the reason we're looking for the upper bound here is if you perform the rule of thumb that I showed you how to do before, we're going to expect this series to converge. So this will always be less than or equal to k plus 1 over k cubed plus 1. And k plus 1 will always be less than or equal to 2k. Because for all k from 1 to infinity, k plus 1 is less than or equal to k plus k, which is just equal to 2k. And so finally here, we have that k cubed plus 1 here, or I should say 1 over k cubed plus 1, will always just be less than or equal to 1 over k cubed, because k cubed plus 1 is a larger integer than k cubed. So 1 over k cubed plus 1 will be smaller than 1 over k cubed. And so finally, this thing right here is going to be less than or equal to 2k over k cubed, which is equal to 2 over k squared. And so this sequence of terms in our series is going to be the ak when we apply this theorem, and this sequence right here is going to be the bk when we apply this theorem. And we then have that the sum of the bk's, or the sum of 2 over k squared from k equals 1 to infinity, converges because it is a p-series with p greater than 1. The p there is actually equal to 2. So from the integral test, we showed that p-series with p strictly greater than 1 must converge. And then therefore, by the direct comparison theorem, the sum of the more complicated series, which is the sum of k plus sine of k over k cubed plus 1, must also converge. So there you have it. It's a relatively straightforward application of this direct comparison theorem. So this example shows the correct way of using it, the DCT, to prove convergence. Let's do an example where we can show divergence, just to show that this can be done and used in either way, depending on what we want. So I didn't do the rule of thumb for the last example. I encourage you to go through and do that, just to kind of get an idea of how to do this. But I will go through and do the rule of thumb for this example. So let's say we have this series, sum from k equals 1 to infinity of 2k over 4 plus 3k squared. So again, just like before, this rule of thumb is not to be used to apply the theorem. We're not directly applying the theorem, but in general, we just want to get an idea of whether or not this series converges, or whether we expect this series to converge or diverge. And the idea here is to look at very large values of k. And for very large values of k, this series is approximately equal to, well, it's 2k over 4 plus 3k squared. And so for large values of k, this is approximately equal to 2k over 3k squared, or 2/3 times 1 over k, which is a divergent series because it's equivalent to the harmonic series. And we know that from the p-test, or the p-series test, the harmonic series diverges. So for very large values of k, this series is looking very similar to a harmonic series, and therefore we expect this series to diverge. So to apply the actual test now, we're going to look at all values of k between 1 and positive infinity. And it's clear that this is a positive series, because 2k is always positive and 4 plus 3k squared is always positive. And what we want to try and do is find a lower bound, which is a simpler series that diverges. And we can do this by simplifying the denominator. So looking for something special here in the denominator. And sure enough, we know that 4 plus 3k squared will always be less than or equal to 4k squared plus 3k squared, or 7k squared. So because this inequality always holds, we also have that 1 over 7k squared will always be less than or equal to 1 over 4 plus 3k squared. Because of this, then, that the inequality, or the lower bound of the terms in our series, is always going to be, so 2k over 4 plus 3k squared will always be greater than or equal to 2k over 7k squared, which is the same thing as 2/7 times 1 over k, which we know is always positive, and we also know that the sum of this series will diverge. So this is the choice for our AKs here. This is the choice for our BKs. And then we know that the series of AKs, the sum from k equals 1 to infinity of 2/7 times 1 over k, this sum diverges. This is because it is a p-series with p less than or equal to 1. It's exactly equal to 1. This is the harmonic series, or 2/7 times the harmonic series. So therefore, by the direct comparison theorem, the sum that we're interested in, which is the sum of the BKs, or the sum from k equals 1 to infinity of 2k over 4 plus 3k squared, must also diverge. Because this series is always greater than or equal to this series right here, and this series right here diverges. And what I mean by that is the partial sums of the series of the BKs for any partial sum, it's always going to be greater than or equal to the partial sums of the AKs. So in the limit, when you get to the full infinite sum, the AKs diverge. The limit of the sequence of partial sums for the AKs diverges, and therefore then the limit of the sequence of partial sums for the BKs must also diverge. So the other test that I want to go over in this lecture is the limit comparison test, or the limit comparison theorem. And this, again, is the limit comparison test for infinite series. So again, like before, we're going to assume that we have two separate series, AK and BK. So AK and BK are both infinite series. And we're going to assume that all of the AKs are positive and all of the BKs are positive for all terms in each one of these series. So if this is true, these two assumptions are true, then we actually have three conclusions. And this is where we have a slightly different scenario than the limit comparison theorem for improper integrals. We can actually say a little bit more with the limit comparison theorem for, or the limit comparison test for infinite series. first result of this theorem is the same as the limit comparison theorem for improper integrals. And that's if the limit as k goes to infinity of the ratio of ak over bk, so the ratio of terms in the ak series and the bk series, this ratio is equal to some limit, right, which is non-zero, positive, and less than infinity, then the sum of the AKs, the series of AKs, and the series of BKs, either both converge or they both diverge. So if the limit of the ratio of terms to of coming from these two series is equal to some limit L, and that limit is non-zero and a finite real number, then the two series have to have the same behavior. So we use this in a very similar manner to how we used it for improper integrals, which is we take our complicated series and we find a comparison series that's simpler and that we can show this limit is equal to some finite value. And then the convergence or divergence of the test comparison series will tell us about the convergence or divergence of the original complicated series. But we also have two additional results of this theorem that we didn't have for the theorem on improper integrals. And that's because sometimes it's difficult to find a comparison series that gives us a finite limit. We can go through additionally and prove that if we can find a comparison series that gives us a ratio limit of 0 and the sum of the BKs converges. So if this is true and this is true, then the sum of the AKs must also converge. And the reasoning behind this is basically if this limit is equal to 0, that means that the BKs are growing much faster than the AKs. So this infinite series of BKs is going to be growing much faster than the infinite series of AKs. And so if this is true and the series of BKs converges, then the sum of the AKs must also converge. And vice versa, we have that if the limit as k goes to infinity of this ratio is equal to positive infinity, which essentially means that the sum of the BKs is growing much, much slower than the sum of the AKs. So if this is true and the summation of our comparison series, the sum of BKs, diverges, then the sum of the AKs must also diverge. And so this is a very, very powerful test, and is going to allow us to go through and directly say a number of different things about any given complicated series of AKs that we can apply this test to. So like before, the proof of this is in the book, and I can go through this with you if you're interested, just to see it. done out. However, right now what I want to just do is go over a number of different examples of how to directly use this test and apply this test. So we'll start with a relatively simple example, and we'll look at the summation from k equals 1 to infinity of 9k squared plus 1 over k to the fourth plus k plus 2. And like before, if we go through and kind of use our rule of thumb to get an idea of whether or not this series is going to converge or diverge. Remember, this is not the same thing as applying the test, but it's just kind of getting an idea of what to expect with this series for large values of k. Because in some sense, this is the behavior of this series for large values of k is what matters in determining the convergence. The series that we have is 9k squared plus 1 over k to the fourth plus k plus 2, which is approximately equal to 9k squared over k to the fourth for very large values of k. So it's approximately equal to 9 times 1 over k squared for very large values of k. And we know that because the series, or the sum of 9 times 1 over k squared, is equivalent to 9 times a p series, with p equals 2, we expect this series to converge, because we know the series 9 times 1 over k squared is going to converge. So this, again, is just kind of to give us an idea of what to expect when applying this theorem. It also, when doing the limit comparison theorem, is helpful to do this because this gives us a direct idea of what function to use for our comparison series. So, just like before, this is the sum of our AKs, or our complicated series. I want to make sure that I'm being very clear here. This is 9, not A. So the AK is 9k squared plus 1 over k to the fourth plus k plus 2. And what we're going to look at is BK is 9 over k squared. We'll look at the limit of AK over BK as k goes to infinity. And this is going to be the limit as k goes to infinity of the AKs over the BK, which is 9 over k squared, which, after a little bit of simplification, is going to become 9k to the fourth plus k squared divided by 9 times k to the fourth plus k plus 2, which after either applying L'Hopital's rule or going through and using some of our limit simplification techniques from Calculus 1, we'll simplify to 1, which is non-zero and non-infinity. This is the L value from the theorem. And so we can conclude then that the sum of our complicated series has to have the same behavior as the sum of our simplified series, because the sum of the bk's, or the sum of k equals 1 to infinity of 1 or 9 over k squared, converges, we can say that therefore the sum of the ak's, or the sum from k equals 1 to infinity of 9k squared plus 1 over k to the fourth plus k plus 2 must also converge by the limit comparison theorem. So we'll do one or two more examples just to kind of make sure that we're understanding how to apply this theorem. So let's say we have the summation from k equals 1 to infinity of k plus 1 over 4k plus 3 to the power k. And as always, we'll kind of start off by trying to use a rule of thumb to determine what the series converges to. Or not what it converges to, sorry, get an idea of whether or not it's going to converge or not. So for large values of k, we know that k plus 1 over 4k plus 3 is approximately equal to 1/4. If you take the limit of k plus 1 over 4k plus 3 as k goes to infinity, you'll get 1/4. So what that means is that for large values of k, our terms in our series is k plus 1 over 4k plus 3 are very, very close to, approximately equal to, or to the k, approximately equal to 1/4 to the k. And we know that the infinite sum of 1/4 to the k converges very nicely. It's the geometric series with r less than 1/4, or less than 1. So the sum of 1/4 to the k is going to converge to 1 over 1 minus r times r, because we're starting here at k equals 1. So because of this, we expect that this series is going to converge, and we're going to try and use this as our comparison function. So remember, this infinite series is the sum of AKs. This is the more complicated series, and we're going to compare this to the infinite series of BKs, where BK is 1/4 to the K. And so we're going to look at the limit as K goes to infinity of AK over BK, which is the limit as k goes to infinity of this function right here over 1/4 the k and we can directly rewrite this a little bit. This limit is going to be the same thing as the limit as k goes to infinity of 4k plus 4 over 4k plus 3 to the power k, which initially may look a little bit daunting, but if you remember the methods that we have from using L'Hopital's rule, whenever we have an indeterminate form like this, which is a 1 to the infinity indeterminate form, because the inside of this exponential is going to 1, and the k here is going to infinity, so this is a 1 to the infinity indeterminate form. In order to deal with this, we instead are going to look at the limit as k goes to infinity of the natural log of 4k plus 4 over 4k plus 3 to the power k, which is the same thing as the limit as k goes to infinity of k times the natural log of 4k plus 4 over 4k plus 3 which is the same thing as the limit of this natural logarithm over 1 over k, and this yields a 0 over 0 indeterminate form, which we can directly apply L'Hopital's rule to. And the only thing that I would say is to remember that when we differentiate this ln of 4k plus 4 over 4k plus 3, this is the same thing as the derivative of natural log of 4k plus 4 minus natural log of 4k plus 3 and this is just from the natural logarithm rule that natural log of a over b will always be natural log of a minus the natural log of b. So the simplified derivative is going to be 4 over 4k plus 4 minus 4 over 4k plus 3. Which, when we bring to common denominator and simplify terms using some basic algebra, ends up just simplifying to negative 1 over k plus 1 times 4k plus 3. And so this is just explaining something that we need here to get the derivative of this numerator with respect to k in order to apply L'Hopital's rule correctly. So the derivative of this numerator is going to be negative 1 over k plus 1 times 4k plus 3 and this is divided by the derivative of 1 over k, which is negative 1 over k squared. So the negatives cancel out, and we're left with the limit of k squared over, and when I expand the denominator here, this is going to be 4k squared minus 7k, plus 7k plus 3, which has a limit of 1/4. When we apply L'Hopital's rule here, and remember what we started with, this is the limit as k goes to infinity of the natural log of the sequence that we're looking at. Therefore, the limit that we're looking for is e to the 1/4, which is non-zero. And therefore, by the limit comparison theorem, and I'll move this all down a little bit to make some more space here. So we have that then the sum of the bk's is the sum from k equals 1 to infinity of 1/4 to the k, which converges. Specifically, we have that this converges directly to 1/4 over 1 minus 1/4. But the main point here is that this series converges, and then therefore, by the limit comparison theorem, the sum of the AK's, which is the sum from k equals 1 to infinity of k plus 1 over 4k plus 3 to the k, so this sum right here must also converge. Because the limit of ratios, ak over bk, is a non-zero constant, and therefore the comparison series has to have the same behavior as the more complicated series, and vice versa. Now, it's really important to me to emphasize again that this does not give us the value of the series of the AKs. We do not know what this value is just because we know that it converges. But this limit comparison theorem gives us that it does have to converge because of the fact that the simpler series of BKs has to converge. Because the limit of the ratios is equal to this L value right here, which is non-zero. So the two previous examples have been examples of directly applying the limit comparison theorem when the limit of the complicated series terms to the comparison series terms is equal to a non-zero value. Remember that you have these other two scenarios that can also happen that are more specific, but sometimes very, very useful as well. So what I want to do is cover one final example, because like I mentioned before, the previous two examples are an application of the first result of the limit comparison test. And I don't think I'm going to have enough time in this lecture to do both 2 and 3 here, so I'm just going to go over an example of how you would apply the second part of this test, because 3 is similar as well. But the main result of part 2 of the LCT is that if you can find for a complicated sequence AK sequence bk that's a simpler comparison sequence or comparison series, such that the limit of the ratio of ak to bk is 0 and the sequence of the bk's converges, then we can conclude by the LCT that the AKs must also converge. The series of AKs must also converge. So this is going to be the final example that I do in the lecture. So for this example, we'll just consider the following function, the following series. This is the sum from k equals 1 to infinity of the natural log of k over k to the 5/4. And I'm going to start by trying to do the rule of thumb. And we're going to do this in the same manner that we did before. And this is going to be looking at what the terms in this series look like for very large values of k. K is very large. So we're going to look at the natural log of k over k to the 5/4 when k is very large. And one of the things that we've actually seen, we've seen this already all the way back to the limits, doing limits, is that the natural logarithm function grows slower than any polynomial function. So it turns out that this is always going to be less than or equal to k to the alpha over k to the 5/4 for any value of alpha. And this is simply because the natural logarithm function grows slower than the monomial power function. Or, put a different way, if you look at the limit, if you take the limit as k goes to infinity for any value of alpha of the natural log of k over k to the alpha, I should say for any positive value of alpha. So this limit is the same thing as when you do L'Hopital's rule, the limit as k goes to infinity of 1 over alpha times k to the alpha, which is equal to 0 if alpha is positive. So what this means is that the logarithm function is growing much slower than k to the alpha. So eventually, for a large enough k, so for large values of k, natural log of k will always be less than or equal to k to the alpha, which is the same as saying natural logarithm of k will always be less than or equal to k to the alpha minus 5/4. And the trick here now is to say, well, if we choose alpha correctly, is there a way to get a convergent sequence right here that's simple to show that it's convergent when we add all the terms in the sequence to get the infinite series? And this can directly, definitively be done. Because if we choose alpha equal to 1/8, noting that 1/8 minus 5/4 is going to be negative 9/8, then we have that the natural log of k over k to the 5/4 will always be less than or equal to k to the negative 9/8, or sorry, less than or equal to, not equal, less than or equal to k to the 9/8, which is 1 over k to the 9/8. And we know that the infinite series generated by this sequence, 1 over k to the 9/8, is a p-series with p greater than 1, so it converges, and therefore we expect this to converge as well. So this was a slightly longer rule of thumb than for the previous problems, but I just wanted to go through and show you that you can definitely do this, and then go through and directly apply the LCT here to get that this series is going to do the same thing as the series of 1 over k to the 9/8. Well, we do have to be careful because this is the special case of the limit comparison theorem where that limit goes to 0. So let's go through and do that, and we'll kind of investigate that. So first we look at the limit as k goes to infinity of our sequence ak of complicated terms over our sequence bk of comparison terms, which is the limit as k goes to infinity of natural log of k over k to the 5/4 over 1 over k to the 9/8, which is the same thing as the limit as k goes to infinity of the natural log of k over k to the 9/8 minus 5/4, which is going to be k to the 1/8 in the denominator. And this limit is in fact equal to 0. So that this limit, the comparison limit, or the ratio limit, is equal to 0, and we have that the sum from k equals 1 to infinity of 1 over k to the 9/8, which you'll remember is our sum of bk's. This converges because it's a p-series with p equal to 9/8, which is greater than 1. So therefore, by the limit comparison theorem part 2, the sum of our ak's, which is the sum from k equals 1 to infinity of natural log of k over k to the 5/4, must also converge. And this is a very neat example, I think, showing how powerful this theorem is, right? You need to know a little bit about the growth rate of functions in order to understand this, but it's relatively straightforward to do if you remember how to do your limits from the very first part of this course. And this is why we kind of start the course by looking at L'Hopital's rule and limits of indeterminate forms, because they're so useful and used when we're going through and applying these tests. But I just want to make you aware that right, this example is the LCT part 1. The previous two examples that we did were the LCT part 1. So this one is the LCT part 1, and then this example was also the LCT part 1. And similarly for the other examples that we did in this lecture, this one was the DCT part 2. And this first example was the DCT part 1. But I think that will conclude the lecture for today. Thank you very much for tuning in. I hope you had a fantastic day and that you learned something.